Our last topic that we're going to cover just real quick is, so far we've assumed that all gases behave ideally, but that won't always be the case. And let's talk about when that's going to be true, that when gases are not going to behave ideally, and also talk about how we can take into account what happens that makes them not behave ideally. And mostly what's going to happen is the assumptions behind kinetic and molecular theory are not going to work anymore. And so this happens when the gas particles get really bunched together. So if they're really, really tightly packed together, this will tend to cause the gas particles to behave non-ideally. So this generally means very high pressures. Or you can think of it also as high density, right? So if the gas particles get pushed closer together, one of the assumptions that we make is that the gas particles take up no volume. And this assumption starts to break down. So they start to crowd out each other, and that breaks down one of those assumptions that underlies the ideal gas law. So this is one situation where you're going to get deviations from ideal behavior. The other one is that if T is low, if the gas particles are moving really slowly, our assumption, and this also applies at the high pressure too, our assumption that there are no attractive forces between the gases also starts to break down. So the slower the gas particles are moving, the more time they have to interact with each other, the more time they spend close to each other. And same thing if the density is high, they're going to be packed tighter together, and so the forces between the gas particles are going to start mattering. They're going to stick to each other, and they're not going to push as much on the pressure is going to be smaller than what you'd expect. So our assumption of the PV equals nRT starts to not work. Now, it's still mostly correct, but we can make corrections to this to account for the non-ideal behavior. And so one of the equations that does this, we're not actually going to use this equation, but I want to introduce it to show you sort of how you could take into account these effects of these assumptions breaking down, is what's called the van der Waals equation. This was actually a Nobel Prize back in the early 1900s for Johannes van der Waals, who came up with this equation. With these underlying ideas that we're talking about, where the kinetic molecular theory breaks down. So we don't really need to make any changes to the number of moles. That is what it is, and temperature as well. That the assumption that it behaves, goes with average kinetic energy is still a pretty good assumption, but it's really pressure and volume we need to take into account. So the van der Waals equation makes a correction to the pressure, P plus n squared A over V squared. And this part here, this accounts for the attractive forces. So the pressure is gonna change because of these attractive forces, and it's going to depend on the density, the square of the density here. So this value A, this is just known as the van der Waals constant, is determined by measuring the gas. So this is something you have to just make a measurement for each gas you want to know this for. The other thing that we can do is add this other term, V minus NB, and then this equals nRT. So it kind of looks like PV equals nRT. We just have a corrective term for attractive forces, and this term, this minus NB term here, this is the non-zero volume of the gas. This actually takes that into account. And so your actual volume is actually a little bit smaller than what you think it is, because some of the space is taken up by the gas particles. And so this B constant you measure to get an estimate of that. And so then you can use an equation like this to correct for the ideal gas law to get, this is sometimes what we call, as opposed to an ideal gas, we call it a real gas. I mean, all gases are real, but this is just the terminology that we use. And so, yeah, that's as far as we're going to get into this. I just wanted to introduce the conceptual idea of non-ideal behavior and how we can take account of it. And with that, that ends Chapter 5 for us.